All right, Paul. So I think I'm not sure if you've illuminated us on what space is, but as near as I can understand, the idea is that space is described by numbers. Every part of space has got a number, and we can
Or
use
three
those
numbers.
numbers, well, three numbers, sorry. Yes, three numbers, and that those numbers can be used to describe essentially how far things are apart by using mathematics. And we care about that because physical laws like gravity and things depend on that distance in number space. And so that's sort of an abstract way of describing space in numbers.
So the crucial thing here is the concept of what we call the metric,
Yep.
which is if you've got two things with their sets of three numbers, to work out how close they are. So let's say I've got x, y, z coordinates of two things on Earth. How do you work out how far apart they are?
Oh, that's easy, because that's just what the Greeks told us, Pythagorean theorem.
Yep.
Whoops.
So here it is. So we're talking about small distances. So the delta means a small difference in x, a small difference in y, a small difference in z. If you had to go a big distance, you just add up all these small differences as you go. And so this is just Pythagoras' theorem, that the distance is equal to the square root of the difference in x coordinates squared, the difference in y coordinates squared, the difference in z coordinates squared. That's just Pythagoras'
So if
theorem.
you have a three-dimensional triangle, it's x, y, z. That's how long the hypotenuse is. And we're going to make sure that our distances are really small here so we can treat everything as a straight line.
Yep, so if you have God's supercomputer and we have lots of things with different sets of numbers, we can use this to work out if they're going to be close, and therefore if one explodes, which things are going to be affected, for example.
Okay, no worries. This is easy.
Yep, so we can simulate the universe this way. But now let's go back to Einstein's problem, acceleration and mass.
Yes.
How can we make acceleration and a force relate to each other? Maybe we need to muck up something. When we talked about Einstein's theory of special relativity in the violent universe course, we came up with the idea of transforms, how you convert from one frame of reference to another, and we did horrible things to it, and that was the basis there. So Einstein was going to be up to it again. What if we start tinkering with this? Could that help us? Could tinkering with
Sounds
this...
to me like it's going to hurt us if we mess around with Pythagoras' theorem.
But there was some mathematics from the previous century that had played with this purely in an abstract way, and Einstein managed to dig the stuff up.
Yep.
And he thought, well, maybe if we muck around with this, it will give us something that can behave like a force.
Okay, so give me an example.
Okay, so let's say we take the equation we had before, square it, but now we're going to change it a little bit. Since we have the normal thing normally,
Yep.
but let's say the delta x crosses an integer boundary. So if delta x is going from 1.3 to 1.4, just use this. But if it goes over an integer boundary, so let's say 1.95 to 2.05, that's crossed an integer boundary, and let's use that instead. So we're going to take the modulus of this, the positive value of that, take off 1 and square it. So
okay.
what's that going to do to our universe?
I think it's going to make us jump around a fair bit when you get to these little edges. Let's think.
Yeah, so here we have our coordinates, x, y, and z, and these are the integer boundaries.
Okay.
So let's imagine we have two things here. What's going to happen there?
Okay, so we have two things here, and let's say one's moving a little bit that way, we're going to move a little bit that way. Well, you move by dx, and so that distance is going to be perfectly normal. It's going to be just what you would expect it, because I'm not on the boundary, and so my metric tells me that the distance I move is just the distance I should move.
Yep, so a particle there and a particle there in God's supercomputer, according to this metric, are going to be close to each other, and so they're going
That's
to
right.
affect each other. So it could be, for example, two atoms adjacent on my ear.
Okay.
And so if one of them goes for a walk, so does the other one, because they're bound together.
Okay?
Okay, but now let's look at, say, imagine we have two particles, one there and one there.
So we're going to be right on side, just one side of 3 or 4 in this case. So just one, like 3.99999 and 4.001. And in this case, if we try to cross that boundary, we jump, right?
Yeah, so if we go back to here, we see delta x is very small, minus 1 squared. So it's going to be about 1 squared, about 1. So not
Right.
very small, it's pretty
So
big.
they're a long ways apart. And so I'm going to go think, at some level you would normally think they'd be right next to each other. But in this case, they're saying they're a long ways apart. It's like this one's almost like being over there.
Yeah, so it means if that one explodes or goes for a walk, it probably won't affect that one because they're not next to each other. They've got
Right.
coordinates that are similar, but the metric has
Right.
changed. They're not going to affect each other.
But interestingly enough, they do affect something else a long ways away.
Yeah, so let's
then.
imagine take these two. What's going to happen now?
All right, so in this case, these things are an integer apart. So if I do boom here, the explosion is going to map not here, but over there.
Yeah, so this one's, let's say, 1.99 and this is 3.01, so they're crossing an integer boundary.
Yep.
And so we have to use this one, so the difference is like 1.01 minus 1. Small number, square makes it even smaller. So it means these two, go back a bit, these two actually are close to each other and they're going to affect each other.
Right.
So what is this giving us?
Well, it's going to give us kind of a checkered universe, I think, where you literally have these boundaries where suddenly everything changes, your universe changes, and you affect things differently. So
Yeah, so it could look something like this.
okay, so yes, so this is yes. It looks to me like a place far, far away, long, long time ago. And so you're literally going to go through and here you affect and you map onto here. And this is lost, except for it maps onto here and it maps onto there. So everything maps on to things that are sort of away from itself, but just, a bit.
So we could actually live in a universe with a metric like this. We wouldn't know.
Well, unless you cross the boundary. And
You can't cross the boundary because if you go here and you're moving that way, you're going to the place which is a small metric away, which means you'll jump to there.
okay. So we would know. It would just look like it's next door to us.
So this could be our universe.
Okay.
That's actually a rather trivial case because it wouldn't even be able to tell the difference in that one. But let's imagine something a bit more seriously weird. Let's, instead of measuring our coordinates in x, y and z, so-called Cartesian coordinates, we can measure them in cylindrical polars. We can measure them any way we like. Cylindrical polar coordinates, you measure, instead of measuring x, y and z, you measure r out, angle and height.
And then you can get to any place you want with that coordinate.
Yes.
Good.
So it's like a gun sight, so up and down, round and round.
Yep.
And so we've got r, theta and z. Now in this case, the metric, if you move the r by a bit, the distance moves by that same amount. So
Yep.
the s squared is just the r squared.
Yep.
Likewise z, if you go up a bit, the distance is also going by that.
Yep.
But theta is a bit different because when you're very close to the centre, an angle change doesn't move you very much. So you get a very small arm, you change the angle, doesn't move very much, but a very long arm, you change the angle, it moves rather more. So you need an r squared d theta squared for that.
So that's just the small angle approximation where the arc is r theta, and that's how much you move. And of course you got to square it here for Pythagorean's theorem.
The same thing we used back in the first course in the series to work out the size of things out in space. So this is our universe, common sense. But let's imagine we get rid of that r squared.
Okay.
So we've now got this. What's going to happen in this universe?
Okay.
So we can look here, we've got angle theta again. Now what's going to happen is, let's say you move from there to there, it's going to be a given change in angle.
Yep.
And moving from there to there is the same given change in angle.
Right.
So those are actually the same ds, the same distance, according to this metric.
All right. So that sounds to me like it's going to change the way you move around in a universe that had this law associated with it.
Yeah, so let's imagine for example we had a light wave coming like this. And if you remember, we talked about in the second course Huygens principle, which says that the light wave, both sides of it are going to move the same distance.
Right.
So this bit will move it at the same, a particular ds, which will get it to there, and that will move the same ds, which will get it round to here.
Right.
And from there, then move like this. So what's going to happen is you get waves spreading out from each point in the waveform, and where they all add up in phase, it's going to move.
Yes.
And that'll be the same ds, which is going to be moving at a constant angle round. So that means the light wave, instead of travelling in a straight line, will go in a circle. Let's go round and round. And the same thing will apply to matter, because matter is quantum mechanical waves.
Right.
So if you tried to walk in a straight line, you'd go in a circle.
Okay, so it is possible that straight lines, or the distance that you would travel, you think as being a straight line, actually ends up being curved if you have that type of metric.
And this is beginning to sound like what we need to make Einstein's idea come true. What we need is something that could accelerate things that doesn't involve a force. And this is getting things to go in a circle, which means acceleration, but there's no force involved. It's just changing the metric. So it's beginning to look like this might be helpful to us.
It's a very tricky solution, but yeah, I can see how it might work.
There are other analogies to this which may help. At this point, normally, most people's brains are dribbling out of their ears.
Yes.
So let's try and make it even worse. We'll have another analogy. One analogy is the hot plate. Let's say we've got a bug living on a two-dimensional universe, which is a hot plate.
Yep.
And let's imagine some parts of this hot plate are hot, and when the bug goes over them, it gets bigger. It expands. Maybe it's a metal bug, so it gets larger when it gets over it.
Okay.
So that's a bit like changing the metric. That means that the distances, ds's, are bigger here than over there.
Yep.
Now if the bug's just going through a cold area, it's got both legs and they both advance the same amount like tank tracks or something, and it will go in a straight line.
Yep.
But now if we move it over there, when it comes over to here, its right-hand legs have expanded
Yep.
because they're in this region with a different metric, the hot plate, whereas the left ones are still cold, and so it's going to turn. So once again, we're getting acceleration without force. We're just changing the metric and making things apparently accelerate.
Okay.
Another way to see it is to imagine two-dimensional creatures embedded in a three-dimensional universe. So let's imagine you're a bug lives on a two-dimensional space. We could imagine curving that space in the third dimension. So let's imagine, for example, we had a light ray coming along here in this curved space. Two light rays like this, you think they just go in a straight line, but this one's actually got to go further because it's got to dip down.
So it's gonna like that. Well, this one's going straight.
So they won't add up in phase here because that one's had to go further. They'll only add up in phase if they curve around, so they've gone the same distance.
Right.
So this one's gone, the one inside has gone the same distance because it's gone down and up. The outer one's gone the same distance because it's gone further around the outside of a circle. So once again, light rays or a particle will move in a curve in a situation like this.
Okay.
So we seem to be getting acceleration without force. If we muck up the metric, it makes things behave rather weirdly.